I'm going to present you decentralized exploration in multi-armed bandits. This is a joint work with Reda Alami and Romain Laroche. Here the outline of the presentation, but let me go straight on the main motivation of this paper. The main motivation of this paper comes from sequential A/B testing use case. It is a very common use case. For instance, Orange Web Portal performs marketing optimization for promoting services. If I would like to promote Orange TV, which banner is the best? Should I push on Game of Thrones or on sports? Just try and then select the best option. This is the sequential A/B testing approach. The framework for studying sequential A/B testing is called the exploration problem. The goal is to find an epsilon optimal arm while sampling as little as possible. In practice, a centralized approach is used. This means that when an event occurs on a user device, it is gathered and processed by a central server which returns the selected arm. This works well. However, there is a devil hidden in the detail. Here it is. All the events can be, or in fact are, logged on store. So the question is, do we really need to gather billions of logs containing private user information for handling sequential A/B testing use cases? Answering this question is the main motivation of this paper. Rather than using a centralized architecture, we switch on a decentralized architecture. Here, the events are processed as close as possible on the user devices. The players are the devices. The players collaborate to find an epsilon optimal arm, and they are allowed to exchange some information through some messages. And when an event occurs on a user device, the player is active. The player chooses an arm and then receives a reward. Finally, the player may update his set of arms and send a message to other players. The goal is to design an algorithm that samples effectively to find an epsilon optimal arm for each player while ensuring privacy and minimizing the number of messages. Here, the communication cost is clearly the number of messages. But I have to explain what I mean by privacy. Here we define the privacy level as the information about the preferred arm of a player that an adversary could infer by listening the message of this player. Definition 3 controls the confidence level 1 minus theta with which the adversary could infer the preferred arm of the player knowing its messages. The higher eta, the higher the privacy protection. Indeed, if eta is high, the only thing that the adversary could infer is that the remaining arm of the player is the preferred arm of this player, but with a small probability, 1 minus eta, which can be much smaller than a random choice, 1 over k. This is our definition of privacy, which is well suited for decentralized exploration and maybe could be extended to other decentralized algorithms. So we have introduced a new problem setting where the players collaborate to find an epsilon optimal arm while sampling as little as possible, while ensuring privacy, and while controlling the communication cost. So now, let me go on an algorithm which handles this setting. The idea of the algorithm is very, very simple. An arm selection subroutine is run on each player, on each device. The players exchange the indexes of arm that they eliminate with a high probability of failure. The high probability of failure ensures privacy of messages. And when in-house players vote for the elimination of an arm, it is eliminated for all players. That's all. It is very simple. So why does it work? Because when M players independently eliminate an arm with a high probability of failure, eta, then the probability of failure of the group of voting players is eta power n, which is pretty small. That's the idea of the algorithm. So now let me formalize a little bit more this idea. Decentralized elimination is a generic algorithm which can use any arm selection subroutine, runs with a failure probability eta, and which returns the set of eliminated arms each time it samples an arm. In addition, an arm selection subroutine satisfies properties 1 and 2. Properties 1 ensures with high probability that the remaining set of arms contain at least one epsilon optimal arm. And property 2 simply ensures that the arm selection subroutine stops. Based on our knowledge, all best arm identification algorithm can be used as an arm selection subroutine. Properties 1 and 2 are useful in the analysis for providing generic proofs. Our first result is Theorem 1. Theorem 1 states that using any arm selection subroutine equipped with properties 1 and 2, decentralized elimination finds an epsilon optimal arm while ensuring privacy and controlling the communication cost. Moreover, Theorem 1 provides us the number of players involved in the vote, the number of players, which is set according to the failure probability of the group of voting players, delta, and eta, the privacy level. Finally, notice that the communication cost is very small, and notably, it does not depend on the number of samples. Our second result is about the sample complexity. Theorem 2 states a generic upper bound of the sample complexity of decentralized elimination. As TPY here is the sample complexity of the used arm selection subroutine, Theorem 2 states that the penalty coming from the privacy and the communication cost mainly depends on P star, which is the probability of the least frequent voting player. So let me illustrate this result on a simple case. We consider here that the distribution of players is uniform and that we use an optimal arm selection subroutine. Then using Theorem 2, we obtain the following sample complexity bound. The left term is the optimal one, is the sample complexity of the optimal arm selection subroutine. So the right term is the penalty coming from the privacy and the communication cost constraints. The good news is that this penalty is additive with respect to the optimal one, and notably it does not depend on the approximation factor epsilon. The bad news is that in the case of uniform distribution, this penalty is linear with respect to the number of players. So let me go on some illustrative experiments. In the first problem, the distribution of players is uniform, while in the second problem, the distribution of players is unbalanced, and half of players generates 80% of events. We compare our approach against two natural baselines. The one privacy baseline runs an arm selection subroutine on each player, but the players are not allowed to exchange information. The zero privacy baseline is the centralized approach, which does not ensure privacy, and which has the maximum communication cost. We have tested two arm selection subroutines here, successive elimination with randomized round robin, which is based on uniform sampling, and successive elimination of suboptimal arms, and UGAP EC, which uses adaptive sampling and a stopping rule to output the best arm. This is an explore then commit approach. For both problems, we have plotted the sample complexity versus the number of players. The first observation is that the performances of one privacy baselines, here and here, are horrendous on both problems. Worse, when the distribution of players is not uniform, when the distribution of players is unbalanced, then the performances of one privacy baselines decrease. That means that the sample complexity increase. Concerning the arm selection subroutine, we see here that one privacy UGAP EC here outperform one privacy SER3. While in the decentralized case, it is the opposite. Decentralized SER3 outperform decentralized UGAP EC. This is due to the successive elimination of suboptimal arms by different groups of voting players. This suggests that successive elimination algorithms are better suited for decentralized elimination than explored and commit algorithm. Finally, if we compare decentralized elimination with the zero privacy baseline, here we see that decentralized elimination suffers from a penalty which is linear with respect to the number of players. But the linear dependency of the sample complexity here is due to the fact that by construction of the two problems, the probability P star of the least frequent players decrease in 1/n, which implies the linear dependency. So forget the linear dependency, it is an artifact of the tested problem. Just we can remark that decentralized elimination is better when the distribution of players is unbalanced. So let me conclude. If we compare this centralized exploration and decentralized exploration, we see that decentralized exploration exhibits numerous advantages. Privacy, by using an epsilon eta private algorithm, a dramatic reduction of the communication cost, which is a strict requirement for Internet of Things applications, increasing the responsiveness of mobile phone application by vanishing the interaction with a central server, and finally, scalability, thanks to the parallel processing. But these benefits are not for free. There is a cost, and the cost is a higher sample complexity. We advocate that decentralized exploration allows a good balance between conflicting interests. The service provider performs sequential A/B testing for optimizing its services while saving resources and protecting privacy of users. We think that it is a fair deal, and this problem setting is particularly well suited for Internet of Things applications. To sum up, we have introduced a new problem setting, decentralized exploration, where players collaborate to find an epsilon optimal arm. We have provided a privacy definition, which is well suited for decentralized algorithm. We have proposed and analyzed a generic algorithm for this problem, decentralized elimination, which ensures privacy with a very low communication cost, while controlling the sample complexity. Our illustrative experiments suggest that the successive elimination algorithms are better suited for decentralized elimination. And as a bonus, thanks to the generality of the approach, we have extended it to the case of non-stationary bandits, but it is in the paper. In fact, there is much more things in the paper. And I finished, but I will be in front of my poster, sorry, this evening. Thanks for your attention.
Any questions?
Okay, so when you're saying that you can use any best harm identification algorithm as subrouting,
Best of our knowledge, eh?
yes. So you don't really need any. I mean, your subrouting to satisfy any condition, or
Yeah. We have two properties. We can use any arm selection subroutine which satisfies properties 1 and properties 2. And in fact, I don't know a best arm identification algorithm which does not satisfy property 1. It remains all the time an epsilon optimal arms in the set of arms with high probability, and the arm selection subroutine stops.
Okay, because I see you need to like your subrouting to satisfy some kind of finite sample complexity.
Yeah.
Right. I mean,
we can do that with a stupid algorithm. Okay, we need a good arm selection subroutine.
Okay, thank you. Maybe we can discuss later for the poster. Thank you.
We have time for a quick question. If there's no, let's thank the speaker again.
Thanks a lot.